Hello, I'm Nikias, Klohr, Head of R&D here at Result, and today I would like to go into the details of our UHF timing system algorithm, which actually gives you the precision of a detection with a passive transponder. So let's get started. Think about it this way. You have your track or road, and you have a setup with a single antenna line going over that road, and you have a transponder passing over that antenna. Now, the question is what actually happens here, and how do we define the precision, and how do we calculate the actual timestamp that is stored as the passing of the transponder or the participant. And on top of that, what happens if you have more than one participant coming through? Let's say we have a second one coming through a little bit later. So, for starters, let's say in our system, the Result timing system, we define the precision of the UHF system with 200 milliseconds. Okay? So what does that actually mean? What does it mean if you have a precision of 200 milliseconds? It means that if you have two participants coming through within less than 200 milliseconds, we are not sure if we have them in the right order. On the other side, if you get two timestamps with more than 200 milliseconds apart, we are sure that the order is correct. So that's what 200 milliseconds actually means. It means more than 200 milliseconds apart, the system believes it knows the order. Less than 200 milliseconds apart, the order might not be correct, and you should have a closer look at your backup line camera or whatever if you need that kind of precision. In most running events, this is not really an issue because you round to 1 second anyway. But if you do higher speed events, you might want to consider this. And if you need more than 200 milliseconds precision, you might be lucky and it works with the UHF transponder. But we would recommend using our active timing system. So let's go into detail what actually happens here. I hope you watched our other video where I explained the UHF basics, what actually happens when you detect it, but I'll repeat a little bit of that. So the antennas on the floor will be switched through, what we call multiplexing, will be switched through at about 40 times per second. So 40 times per second there's a chance to actually detect the transponder. Every time we detect the transponder, we store what we call RSSI value. That's a received signal strength indicator, telling us how strong we received the signal. And then basically what the system does, it plots that signal strength over time. So let's say we have the RSSI here and time here. What happens if you look at one of those two transponders is that we get some signal strength values, maybe something like this, when the transponder passes over the line. Obviously you can connect that, try to draw a line through that, let's say something like this. And now the goal of the algorithm trying to figure out the timestamp for that passing is to find this peak here. So there is one important setting in the timing system that is called the reaction time. How does this actually work? So what the system always does is, every time it gets a new detection in, it is waiting for the reaction time if there is another detection coming in with a higher RSSI value. So let's say we are the algorithm and we got that first detection in. And we wait, and we wait for the reaction time, which might be as long as this. And we got a second one, so we wait again, and we got another one. Here it gets interesting because the next value is lower than the value before. So we basically skip that value and wait. But then we have another one here. Let's say we wait here, we wait here. We skip this again, we wait here. And then we are here at the top. And here we wait till this point in time. So actually at this point in time, we store the passing with this here as our timestamp for the passing. Okay, so this point here is the time we want, and this is the timestamp we save, but we save it after the reaction time. Typically this is 850 milliseconds. This is the default setup of our decoder, which means that after the participant has crossed the finish line, you will have to wait another 850 milliseconds until the passing actually appears in the memory so that you can use it for further calculations, put it on your lists, or present it on a live TV screen, or whatever you do with it. Obviously, if you short that reaction time, let's say to a very short 100 milliseconds, you may run into the problem that at this location here, the algorithm will decide that it's already over and would store this time. So it's always a compromise between precision, waiting for another higher value, and the reaction time, so the time it takes till you can get the information out of the system. Now this is a typical curve from a runner. The thing is that if you look at a runner, the body movement is not constant, and obstacles like arms are not constant. So you will get a pattern like this. I draw the same thing for a cyclist with a chip on the handlebar. Normal MTB bit mounted to the handlebar where the movement is linear and the surroundings of the chip is constant. There you will more likely find a thing looking like this, where actually even a short reaction time will not suffer your detection precision, because the next value is always higher until the tipping point where we want to capture the timestamp. So depending on the kind of sport that you do, you might want to have a shorter reaction time. Actually, this is quite handy because for sports which are quick, like road race cycling, mountain biking, things like that, you tend to have more things like this going on, where you can have a shorter reaction time. In sports where people are slower, especially running, you want to have a higher reaction time, but it does not really matter because you don't need the time stamp as quick as possible. 1 second normally is more than plenty. Okay, now some of you may have noticed that we have a new detection algorithm on our decoder. If you have not noticed it, you should update your decoder, get the newest firmware. We always recommend to do that because we always fix bugs and introduce new features. So get your decoder updated if you have not noticed the new detection algorithm. But let's go into the details. Why did we introduce that? So actually there is something more going on here. Once we decided that we want to use this timestamp, we ignore the chip for what we call the dead time. Okay, so let's say this period here is the reaction time, and this period here is the dead time. If the chip would appear again, let's say we get another detection, something like this, because the participant chooses to come back over the finish line, or whatever stops on the finish line, things like that can happen. The chip is basically just ignored. We just say, we don't see this chip, we don't generate anything for this chip. You will not get a passing for that participant. The dead time default setting is 5 seconds, and it's proven to be quite good. It just keeps you from generating rubbish data, additional data that you don't really want to have in your timing software. But there's one problem. Actually, at a start situation. At a start situation, you have people standing on the line. And if you have people standing on the line, they will be captured all the time. And the algorithm will try to make sense of this. And actually, the algorithm can only work precisely if people are moving. If they are not moving, if they're standing on the line, all of this doesn't really make sense. But what you normally want in a start situation is the last time that somebody was seen on the mat. Because if you want to do net times, you want to do a difference between start and finish, and you want to do that for the first row of participants too. So you want to know the last time that a transponder was actually seen on the mat. So the new timing algorithm actually works this way. It does the normal operation, so for all your finish lines, split times, things like that, it does the normal operation. But then within the dead time, as long as it continuously sees the transponder, it will always push the dead time forward like this and like this, and lengthen it as long as the transponder is within reach of the antenna. And as soon as the dead time is over and the transponder is not seen anymore, it will store the timestamp, this would be this one here, of the last time that it saw the transponder. This gives you a start time. So when the transponder is moved quickly, you will only have one single detection with this timestamp here. But if the participant chooses to stay over the loop, over the antenna mat, it will create a first time, which basically is the time of when he arrived at the mat and the highest precision that we can get. And then you will get a second detection later on when he moved away again. This way we can capture precise start times. The old way of doing it, where we were just ignoring the chip for 5 seconds, led to highly imprecise start times, because you always had 5 seconds where you didn't detect the chip at all. So normally you had to use the gun start time for the first row of participants in that scenario. So this is the new algorithm. One last thing that I would like to talk about is 2-line setups with 1 decoder box. So let's go back to this here again. Normally you would connect this one line, let's say this is a split somewhere, to 1 decoder box with your cables, and that's it. Sometimes, for redundancy with one single chip, people choose to do a setup where you have 2 lines. Now this is not to scale, okay? So you have one line like this and a second line like this, both connected to 1 decoder box. Basically, the flexibility of our antenna mats allow to do this, because you can split the antenna mats at any given point and create a situation where you have half an antenna mat and another half of an antenna mat connected to 1 decoder box. Now it is very important to understand that the decoder box does not know that you have 2 lines. It always assumes that you have 1 line. So if you do something like that, you might run into problems with this, because if you look at the algorithm and how it works, the decoder will pick up the transponder. Let's say transponder goes over like this. And in this scenario, it will pick up the transponder a first time, giving it a first peak and then a second peak. Let me draw this very quick. So it could look like something like this. Now, depending on your setup, and depending on the antenna and the cable length and how the transponder is mounted, those two might be at exactly the same height or might not. could be small differences between those two. Now the big problem here is that if your reaction time is set to longer than it takes to get from here to here, so I'll draw that again. Let's say your reaction time is set to this. Then depending on the signal strength, the timing system will sometimes pick this one because it was the strongest one, or pick this one because it was the strongest one. As most transponders will be picked up by both lines, this can create a imprecision. So it is important to understand that this distance between the two lines should be longer than your reaction time for your quickest participant. So let's say you put them apart 2 meters, something like that. You should estimate how long will it take for my quickest participant to come from one to the next line, and then you should set your reaction time to a value shorter than that, so that you always get him on the first of the two. At the end, this here also explains a little bit that obviously the precision of all of this is limited. If we go back to what I described in the last video about blocking the transponder with your arm, imagine you have a participant blocking the transponder on his arm on this side here, and that's actually the main reason why you have two lines anyway. If that happens, if the transponder is blocked on this line and only picked up on this line, and for another participant the transponder is blocked on this line but not on this line, obviously the times will not be correct. So it can happen that if two participants come through at the same time, basically at the same time, and one has blocked his transponder here and the other one has blocked his transponder here with his arm, that this participant wins, even if they are at exactly the same time. So it's just important to understand all this so that you know what the limitations for the precision of the UHF timing system actually are. Especially setups like this should not be done if you are aiming for very high precision. If high precision is your goal, you should set up 2 different decoders, and you should also compensate in your software for the delay from one line to the next. But in the end, to be honest, if you want high precision, use our active system, because that's actually why we did it. The passive system just does not give you the precision that you need if you want to do high-profile cycling sports, triathlons, things like that. Use the active system if you are aiming for high precision. So again, this was a very technical video. I hope that you like this kind of video. Please comment in the comments below if you think we should do more videos like this. If you don't, we will go back to the normal style of videos. If you like it, I'm happy to explain more things like that. There's lots of things that we do here at Race Result that are actually under the hood of what you use every day. And on the different discussions I had on our distributors meeting and on our customers meeting, international and German customers meeting, I got the understanding that people are very interested to understand how this actually works. So comment if you like it. If you don't comment, we will just go back to the normal videos. Thanks for watching.